This video introduces one of the most important concepts in chemistry, the mole. The mole is the SI unit for quantifying the amount of matter, and it is used as the chemist counting unit. By now we know quite a few things about atoms, molecules and ions. We know that they're very small, of the order of picometers, and the nuclei of the order of femtometers. We know that their masses are also very small, of the order of 10 to the minus 27 kilograms up to 10 to the minus 25 kilograms. And we also know that their numbers are huge. Even very small samples of matter, for example, a teaspoon of water contains that many molecules of water. A cube of sugar contains that many molecules of sucrose. These numbers are just way too large to deal with in everyday accounting. But we do need a way of counting them. We do need a way of accounting for the very large numbers of atoms, molecules and ions that we see in everyday samples of matter. And that's because chemistry and chemical equations basically involve counting amounts. For example, here's a chemical equation for the combustion of methane, and it's a quantitative expression that one molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. The problem is, even the smallest samples contain huge numbers of atoms, molecules or ions. You're never going to start with 1 molecule or 2 molecules or even a few molecules. You're going to start with trillions upon trillions upon trillions of molecules. So to deal with such large numbers of atoms, molecules and ions, we introduce the SI unit for amount called the mole. Now, the technical definition of a mole is the amount of matter that contains as many objects as the number of atoms in exactly 12 grams of carbon-12. Now, it's not a coincidence that the definition of the mole is linked to the carbon-12 isotope, in the same way that our definition of atomic mass units was also linked to the carbon-12 isotope. And we'll see in subsequent videos how that link arises. For now, the number of carbon-12 atoms in 12 grams of carbon-12 is approximately equal to 6.022 by 10 to the 23. So 1 mole can be said to be equivalent to 6.022 by 10 to the 23 objects. So for example, 1 mole of carbon-12 would be equivalent to 6.022 by 10 to the 23 atoms of carbon-12. 1 mole of oranges would be equivalent to 6.022 by 10 to the 23 oranges. 1 mole of paper clips would be equivalent to 6.022 by 10 to the 23 paper clips, and 1 mole of water would be equivalent to 6.022 by 10 to the 23 molecules of water. Now, the mole is simply a counting unit, and students of chemistry often get confused simply because it's a large number. But the concept of counting units you are already very familiar with. For example, you know the counting unit of a pair. You know that 1 pair of anything, for example 1 pair of shoes, is equivalent to 2 shoes. You also know that 1 dozen eggs is equivalent to 12 eggs. And you know that 1 gross of pens is equal to 144 pens. And 1 ream of paper is equal to 500 sheets of paper. And these are all convenient counting units that we use to quantify large or relatively large numbers of objects. In chemistry, we use the mole to quantify large numbers of objects. 1 mole of water would be equivalent to 6.022 by 10 to the 23 molecules of water. The mole is the SI unit for the amount. As I said, it's a counting unit. These other counting units are valid counting units as well. They just don't happen to be the standard recognised SI unit for quantifying amount. 6.022 by 10 to the 23 is such an important number in chemistry. It's given its own name. It's called Avogadro's number, and it's named after Amedeo Avogadro, who was important in developing the concepts of quantifying the amounts of atoms, molecules and ions. And it has its own symbol as well, Na. 6.022 by 10 to the 23, Avogadro's number. We really need to commit this to memory to 4 significant figures, 6.022 by 10 to the 23. So 1 mole of anything equals 6.022 by 10 to the 23 objects. 2 moles would be twice that number, 2 times Avogadro's number. When we put 2 times Avogadro's number into our calculator, we get the number 1.204 by 10 to the 22. Half a mole would be 1/2 times Avogadro's number, and so on. 1/2 times Avogadro's number happens to be 3.011 by 10 to the 23. If we had any number of moles, for example x moles, then the number of objects that we would have, or the number of atoms, molecules or ions, would be x times Avogadro's number. Now this concept is very important because there are many occasions where we actually want to be able to interconvert between the number of moles of matter and the number of particles. So converting between, for example, number of moles and the number of atoms, molecules or ions. If we started with the number of moles and we wanted to work out how many atoms, molecules or ions we had, we would simply multiply by Avogadro's number. If on the other hand we started with the number of atoms or the number of molecules or the number of ions and we wanted to work out how many moles we had, we would divide that number by Avogadro's number. So here's a typical problem that you might get in chemistry. How many sodium atoms are in 0.234 moles of sodium? In order to answer this, we take 0.234 moles and we multiply it by Avogadro's number. And it's interesting to note the units here. 0.234 moles times 6.022 by 10 to the 23 atoms per mole. We'll see that the moles cancel out, leaving us with just 1.41 by 10 to the 23 atoms. Doing the reverse, how many moles of sodium atom in a sample that contains 8.93 by 10 to the 24 sodium atoms? Well, we would take the number of atoms and divide it by Avogadro's number. So the number of moles in this case would equal 8.93 by 10 to the 24 atoms divided by 6.022 by 10 to the 23 atoms per mole. And that ends up giving us 14.8 moles. So this definition of the mole, the amount of matter that contains as many objects as the number of atoms in exactly 12 grams of carbon-12. And that number to 4 significant figures happens to be 6.022 by 10 to the 23. It seems such a peculiar definition for quantifying the amount of matter. And in the follow-up videos, we actually see why we've defined the mole in such a way